First, the bad news. SAP Business AI won't help you generate cubist versions of your family's holiday photos. But it will help you understand which supplier is best to help you roll out your plant-based packaging in Southeast Asia, or identify the training your junior project manager needs to rise up the ranks, and automate repetitive tasks while you focus on big innovations, so you can be ready for the next opportunity. Revolutionary technology, real-world results. That's SAP Business AI.
This episode is brought to you by Seed's DSO1 Daily Synbiotic, a 2-in-1 probiotic and prebiotic formulated with 24 clinically and scientifically studied strains to support healthy regularity and your gut, immune, and skin health. Optimize your gut health. Visit seed.com/Spotify with code SPOTIFY for 30% off your first month of Seed's DSO1 Daily Synbiotic. These statements have not been evaluated by the Food and Drug Administration. This product is not intended to diagnose, treat, cure, or prevent any disease.
This is SpaceTime, Series 26, Episode 61, for broadcast on the 22nd of May, 2023. Coming up on SpaceTime, a new way to measure the expansion rate of the universe, understanding the Earth's abrupt glacial transitions, and millions axed from spaceport investment in the federal budget. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have developed a new way to determine the Hubble constant, a key measurement of the universe's rate of expansion. The cosmos and everything in it is expanding out from the Big Bang, which began about 13.82 billion years ago. We know it's expanding because we can see that the more distant galaxies are all moving away from us, and the more distant they are, the faster they're moving. It's a quantity astronomers refer to as redshift, and the number is the Hubble constant. It's named after Edwin Hubble, who first realized the universe was expanding. And it's important because it will help scientists determine the ultimate fate of the universe. Will the cosmos keep expanding forever until the stars in the sky are all too far away to see, leaving the heavens black as ink, what astronomers refer to as the Big Freeze? On the other hand, if the rate of expansion is slowing down, then eventually it could create some sort of a steady state, where things basically stop moving away from each other and the universe remains the way it looks today. Or will the universe's rate of expansion eventually stop, with gravity taking over and then slowly drawing everything back together again in a sort of big crunch? And so, you see, knowing the Hubble constant and how it changes over time really is important for answering one of science's biggest, if not the biggest question of all. What is our ultimate fate? The problem is, measuring cosmic distances, and hence the rate of expansion of the universe, is really difficult. Now, thanks to data from a magnified multiply imaged supernova, astronomers have successfully used a first-of-its-kind technique to measure the expansion rate of the universe. Their data provides new insight into a long-standing debate in the field of cosmology, and it could help scientists more accurately determine the universe's age and therefore better understand the cosmos. The work has been divided into two papers, one published in the journal Science and the other in the Astrophysical Journal. Right now in astronomy, we have two precise measurements for the expansion rate of the universe, the Hubble constant. One version is calculated by observations of supernovae, while the second uses the cosmic microwave background radiation that began to stream freely through the universe shortly after the Big Bang. However, there's a problem. You see, these two measurements differ by about 10%, and that's causing widespread debate amongst physicists and astronomers. Now, if both measurements are accurate, it means science's current theory about the makeup of the universe is incomplete. The study's lead author, Patrick Kelly from the University of Minnesota, says if the new independent measurements confirm this disagreement between the two measurements of the Hubble constant, it would become a chink in the armor of science's understanding of the cosmos. Kelly says the real question here is whether or not there's a possible issue with one or both of the measurements. The work by Kelly and a huge team of international colleagues addresses this problem by using a new, completely independent and different way to measure the expansion rate of the universe. Instead of supernovae and cosmic background radiation, the authors were able to calculate the value using data from a single supernova discovered by Kelly in 2014. But this was a special supernova. It was the first example of a multiply imaged supernova, meaning the telescope captured 4 different images of the same cosmic event. After the initial discovery, teams around the world predicted that the supernova would reappear in a new position in 2015, and the University of Minnesota team detected this additional image. Now, the reason these multiple images appeared was because the supernova, they're exploding stars by the way, was gravitationally lensed by a galaxy cluster in front of it. It's a phenomenon first proposed by Albert Einstein in his theory of general relativity. SpaceTime causes mass to bend light, which means that the foreground galaxy cluster has so much mass in it that it's physically acting like a lens, magnifying and bending the light from the background supernova. And because the same light is using several different paths to reach us, thanks to the magnifying galaxy cluster, it has to travel different distances and therefore reaches us at different times. In this case, we're actually getting 4 separate images of the same cosmic event. By using the time delays between the appearance of the 2014 and 2015 images, the study's authors were able to measure the Hubble constant using a theory developed in 1964 by Norwegian astronomer Serge Rafdal that had previously been impossible to put into practice. Now, the new findings don't absolutely settle the debate, but they do provide more insight into the problem, and therefore bring astronomers and physicists closer in obtaining a more accurate measurement of the universe's age. One of the study's co-authors, Brad Tucker from the Australian National University, says the new measurements for the Hubble constant favours the value of the cosmic microwave background radiation, although it's not in strong disagreement with the supernova value either. Tucker says if observations of future supernovae that are also gravitationally lensed by clusters yield similar results, then it would identify an issue with our current supernova value, or with science's understanding of galaxy cluster dark matter.
So the Hubble constant is the term we use for measuring the growth rate or the expansion or the speed of the universe. So this is the standard of saying this is how fast the universe is growing at a point. It's the universe's speed. Now, it's obviously named after Edwin Hubble, who used Cepheid stars and other galaxies to measure and show that the universe was indeed expanding. And so this has always been a critical measurement to understanding the properties of the universe and getting it right. So finding new ways, new techniques, and better ways, in fact, better techniques to measure this speed has been critical for astronomers.
Cepheid stars or Cepheid variables, these are very specific types of stars, aren't they?
That's right. So these are a variable star that has a very specific pulse. And Henrietta Leavitt in the early 1900s showed that there is this relationship, which we now call the Leavitt law, between the pulse, so how long it takes this star to pulse, and then how bright it gets. That there's a very regulated, regular relationship between the two. And this is critical. This gives us something we call a standard candle, meaning we can measure a property of a celestial object, and by looking at this timing, the differences in brightness between the pulses, use it to actually get a distance to it using the whatever our square law, meaning you know how bright something is, you can measure how the light fades with distance roughly.
It's like looking at a bunch of streetlights down the road.
Exactly. If you know how bright the streetlight is right next to you, you can measure how bright the streetlight at the end of the road appears. And if you know it's the same bulb, you can figure out that distance. And that's exactly the same technique. But the problem is, how do you know the intrinsic brightness when stars have all sorts of different sizes and properties? Well, the Cepheid, with this relationship, gave us a way of finding a consistent way of understanding its brightness. Therefore, then, we can measure a distance, and over time, if you look at the distances, you can measure the growth or speed of the universe.
And another option, rather than Cepheid variables, would be type 1a supernovae.
Exactly. And in fact, a project I've been on, we've been trying to find Cepheids in galaxies and then type 1a supernova in those galaxies, because the type 1a supernova, we can see over much further distances to the Cepheids because the stars themselves aren't that bright, so you can only see them in a handful of galaxies. Now, the type 1a supernova supernova, we can see over large distances. And so by finding galaxies that have both, we can do what's called the cosmic distance ladder, and that is have one accurate distance measurement and then calibrate it to another and then keep going that far. That's the technique Brian Schmidt originally used to measure and show that the universe was accelerating. It wasn't just growing, it was speeding up in its growth.
As well as using these cosmic distance markers, there's another method.
Exactly, and this is critical, and that is what we call the CMB, the cosmic microwave background, this relic light, the leftover light or radiation that kind of permeated, went everywhere through the universe 380,000 years after the Big Bang. And if you can measure and model this light, you can actually measure the speed of the universe at the very beginning, essentially, or as the beginning as we can get. And so this is an important measurement. You can understand, well, what is the speed now? We can check against the speed at the beginning. And the problem is the answers don't agree. As in what we measure with Cepheids and supernova, what we measure with the cosmic microwave background, the answers differ as much as about 10%. And that actually is enough to create some problems and consternation for us. What's going on? Are we messing up? Is there something we're missing? Or is something else at play in the universe?
I take it it's not just something as simple as time being measured differently in today's universe compared to what it would have been 13.8 billion years ago or something along those lines.
Yeah, exactly. It's there's a lot of things that go into the model of what the universe is. The ratios of dark matter to dark energy, the properties, the kind of growth rate of as a whole as the universe, and then our understanding of the tools we use as well. That's always simple. We are doing complex measurement. We may have gotten something wrong along the way. These are all very likely scenarios, but is it the CMB measurement wrong? Is the Cepheids measurement wrong? Is it both? Is it something else? A lot of these are huge questions. So looking for different tools is key to see and point us in the right direction.
And part of the job has been to get these measurements as precise and accurate as possible. The trouble is, as we're doing that, the difference between the two measurements isn't getting smaller, it's getting larger, it's getting more confirmed.
Exactly. In the Shoes project I was on, when we did improve the Cepheid supernova measurement, the answer didn't change. It was just the uncertainty, as you said. So it got stronger, this difference. So when we keep finding better ways of improving these measurements, understanding what errors or problems may go in and fixing them, the answers aren't budging, just our uncertainty is getting smaller. Now, the uncertainty getting smaller and the error getting smaller is a good thing, but the fact that these answers aren't getting closer together is leading to the idea more and more that maybe something else is at play.
So how do these new independent measurements fit in?
Yeah, so with this new technique, we looked at one particular supernova Russell. Now, this was really cool because this supernova exploded, or we detected its explosion back in 2014, but it happened to be behind a cluster of galaxies. And as Einstein's predictions say, something called gravitational lens happening, meaning if you have a lot of mass in an object or an area, which is a lot of gravity, that gravity can bend and magnify light. Now, the great thing about it was the supernova happened to happen behind this area. So instead of seeing one supernova, we saw multiple appearances of supernova. In fact, we've seen 5 now appearances of the same supernova. Now, this is really cool because you have the same object that happened at the same point in space. But as it appears at different times to us, it's because that light has taken a slightly different path around the magnifying lens. It's as if one train left the city and went straight to the next city. Another took a detour via the coast, another via the mountains, another did a few stops along the way. Supernova leaves and arrives at the same point in space, but it takes a different path through space, meaning the only thing that changes is the growth of the universe, allowing us a different way to measure the growth of the universe.
And what did you find?
So we found that the answer was closer to the CMB result, even though we should have gotten an answer closer, we thought, to the supernova result. So we got about 73.8 kilometers per second per megaparsec. That's the way we measure this Hubble's constant. How much in kilometers per second and essentially 1 million parsecs of the universe grow. We take a chunk of the universe and measure a speed. And so the fact that we got this answer closer to one of them, it's hard to say what is the meaning. It's one of those things you would like it to say, hey, we clearly understand now what's going on. We don't. Is it, again, that there's something wrong with the measurement? Is there something that changes in the universe that kicks in a speed differently? But I think at the end of the day, we at least have a different measurement along the path of understanding, is this a measurement error or is this something different? And the fact that we got close to one of those answers instead of something completely different shows that actually probably maybe it's not a measurement error, but maybe there's just something else about the universe we're not understanding.
I think when we look at type 1a supernovae, we're finding more and more. The idea with type 1a supernovae is that they all explode with exactly the same amount of luminosity and brightness. And therefore, if you know how luminous it is, and you can see how bright it is, you can determine its distance. What we've been finding in the last decade or so is that type 1a supernovae don't actually all explode at exactly the same mass.
That's exactly right. There's different types, actually, of type 1a supernova now, and this is a big effort we're trying to understand is what are the actual explosions of the stars and how does it relate to the energy being output, which then is that understanding of the brightness of the bulb. So there's still a long way to go, and none of this means that things like dark energy or dark matter go away. It actually shines a light that's saying, hey, these things actually kind of clearly exist from a different measurement, but there's a lot more understanding into what they actually are that we have to go.
What do you draw out of this? How has this changed you in your view of the universe?
I think the cool thing is that every time we get one of these measurements, it's not a straightforward case of understanding it. And this is the beautiful thing, I think, about cosmology, the study of the universe as a whole. It's very unique compared to every other science. We have one of them. Right? Even stars, we have trillions of stars in the universe. We have trillions of galaxies, even more planets. We have one universe, at least, that we know of. And so a lot of our understanding and modeling is quite interesting because in some ways, we may be understanding the properties of what a universe could be, but it doesn't mean that's what our universe is, or vice versa. In our understanding of what our universe actually is, maybe universes can come in different shapes and sizes and flavors. And so this is a beautiful thing of studying the properties of the universe, is that it's a very different way of thinking scientifically than, say, any other field, even other aspects of astrophysics.
That's Brad Tucker from the Australian National University. And this is SpaceTime. Still to come, understanding the Earth's abrupt glacial transitions and millions axed from spaceport investment in the federal budget. All that and more still to come on SpaceTime.
This episode is brought to you by Seed's DSO1 Daily Symbiotic, a 2-in-1 probiotic and prebiotic formulated with 24 clinically and scientifically studied strains to support healthy regularity and your gut, immune, and skin health. Optimize your gut health. Visit seed.com/Spotify with code Spotify for 30% off your first month of Seed's DSO1 Daily Symbiotic. These statements have not been evaluated by the Food and Drug Administration. This product is not intended to diagnose, treat, cure, or prevent any disease.
A new study has supported the long-hypothesized Milankovitch cycles, which are thought to control major swings in planet Earth's climate. Milankovitch cycles are named after the Serbian geophysicist and astronomer Milutin Milankovitch, who in the 1920s hypothesized that variations in the Earth's orbital eccentricity and the planet's axial tilt and precession resulted in cyclic variations in the amount of solar radiation reaching the planet's surface. The Earth's seasons occur because of a tilt in Earth's spin axis, which is inclined by 23.4 degrees in relation to the Earth's orbit around the Sun. Now, generally speaking, Earth's axis always points to the same position in deep space, regardless of the Earth's position in its orbit around the Sun. So, on the day of the December solstice, Earth's south pole is tilted towards the Sun, so the southern hemisphere ends up getting more daylight and more direct sunlight, so it's hotter, and that means the southern hemisphere is experiencing summer. 6 months later, during the June solstice, it's the North Pole which is tilted towards the Sun, and so the northern hemisphere experiences summer, while the southern hemisphere gets less daylight, longer nights, and the sunlight strikes the surface at a shallower angle, meaning less heat, and so the southern hemisphere is now in winter. In between these two, we have the March and September equinoxes. That's when the northern and southern hemisphere get roughly equal amounts of daylight and heat, giving us the seasons of spring and autumn. However, while I said the Earth's axis always points to the same direction in space, regardless of Earth's orbital position around the Sun, that's really only true in terms of our day-to-day lives. Over much longer timescales of thousands of years, a gravity-induced effect known as axial precession causes a slow and continuous change in the orientation of Earth's rotational axis. You can see the same effect in the precession of a spinning top or a gyroscope as the spin axis gradually traces out a pair of cones joined at their apexes. Earth's axial precession is known as the precession of the equinoxes because the equinoxes move westwards along the ecliptic relative to fixed background stars. The ecliptic is the plane created by the Earth as it orbits around the Sun. This slow precession means that over 25,772 years, the positions of the south and north celestial poles appears to move in circles compared to space-fixed background stars. So, while today the star Polaris lies approximately at the north celestial pole, this will change over time, with Gamma Cephei becoming the pole star in about 3,200 years from now. Of course, it also means the seasons slowly move through different calendar months, but we make adjustments in the calendar to compensate for that. And like axial precession, Earth's orbit also changes gradually over time, getting more or less elongated, meaning changes in perihelion and aphelion, when the Earth's at its nearest and most distant orbital positions from the Sun. See, instead of being a perfect circle, Earth's orbit around the Sun is slightly elongated, and the amount of elongation changes over time. In fact, even the tilt of Earth's spin axis changes over thousands of years. Right now it's 23.4 degrees, but in the past it's been both much more than that and far less. Proxy data, that's indirect records of the Earth's climate found in unlikely places like coral, pollen, trees and sediments, show interesting oscillations approximately every 100,000 years, starting about 1 million years ago. Strong changes in global ice volume, sea level, carbon dioxide concentrations, and surface temperature all indicate cycles of long, slow transition to glacial periods and then abrupt switches to a normal and short interglacial period. This idea suggests there may be some sort of predictability in the long-term climate, a notoriously complex system. Now, a report in the journal Chaos proposes a new paradigm to try and simplify the verification of the Milankovitch hypotheses. The study's lead author, Stefano Perini from the Parthenope University of Naples, says he wanted to characterize and illustrate the Milankovitch hypotheses in a simple, elegant, and intuitive way. Many models suggest that Milankovitch is correct. However, such methods are often extremely complicated and detailed, hard to explain, and they incorporate climate feedback loops. For example, increased ice cover reflects more radiation back into space. That leads to further cooling and more ice cover. And this means an abrupt jump in climate only occurs once a specific parameter reaches a given tipping point. Perini's so-called deterministic excitation paradigm combined the physics concepts of relaxation, oscillation, and excitability to link Earth's orbital parameters and the glacial cycles in a more generic way. The relaxation-oscillation component describes how the climate slowly returns to its original glacial state after it's been disturbed. At that point, the excitability piece of the model captures the external orbital changes and triggers the next glacial cycle. By using his own threshold crossing rules and adapting a classic energy balance model, Perini obtained correct and robust timings for the most recent glacial cycles. In fact, it can explain the timing of at least the last 4 glacial terminations. Perini now plans on extending the same analysis to the whole Pleistocene epoch in order to determine its accuracy over longer timescales. He believes similar methods could be used in other fields of nonlinear science and in connection with other climate phenomena. This is SpaceTime. Still to come, millions quietly axed from spaceport investment in the federal budget. And later in the science report, the World Meteorological Organization says there's a 98% chance of setting a new global heat record in the next 5 years. All that and more still to come on SpaceTime. Well, you probably didn't hear this in the mainstream legacy media, but the federal budget handed down last week has quietly axed $32 million from Australian spaceport development. The cut by the Albanese government is part of $77 million which have been slashed from science, including a key part of Australia's involvement in the Moon to Mars Artemis program. Now, these are all crucial aspects of Australia's STEM, science, technology, engineering and mathematics future under the previous coalition government. The Australian Space Agency Spaceport Investment Program was designed to mimic similar projects overseas, allowing the nation to share in the multi-trillion-dollar global space industry which Australia helped pioneer over 60 years ago. Now, when the money was first allocated, ASA says that the funding would provide opportunities to advance technology and increase operational experience with multiple space flights from Australian soil. That funding would have helped Australia regain spaceflight qualifications, which it lost in the 1970s with the downgrading of the Woomera rocket range in outback South Australia from orbital flights to ballistic sounding rockets. Remember, at one stage, Woomera was the busiest spaceport in the world other than Cape Canaveral. Federal Labor Science Minister Ed Husak dismissed the funding cuts, claiming the projects simply don't align with the Albanese government's priorities. To a bit of good news now. Black Sky Aerospace has got approval to develop a new facility in southern Queensland which will both manufacture and test fire rockets and missiles. The complex will include research, development and manufacturing facilities, as well as rocket motor test beds and associated fueling infrastructure. Black Sky recently began producing ammonium perchlorate, a key chemical used as an oxidizer in solid fuel rocket motors. When ignited, the oxygen from ammonium perchlorate combines with aluminum to produce aluminum oxide, aluminum chloride, water vapor, nitrogen gas, and lots of energy, which causes the water vapor and the nitrogen to rapidly expand, creating thrust. This is SpaceTime.
First, the bad news. SAP Business AI won't help you generate cubist versions of your family's holiday photos. But it will help you understand which supplier is best to help you roll out your plant-based packaging in Southeast Asia, or identify the training your junior project manager needs to rise up the ranks, and automate repetitive tasks while you focus on big innovations, so you can be ready for the next opportunity. Revolutionary technology, real-world results. That's SAP Business AI.
Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more. Momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
And time now to take a brief look at some of the other stories making news in science this week with a science report. The World Meteorological Organization is warning that there's a 98% likelihood that at least one of the next 5 years will be the hottest on record, thanks to the combination of El Niño and climate change. The latest global annual to decadal climate update also warns that there's a 66% chance that annual global surface temperatures will at least temporarily exceed 1.5 degrees Celsius above pre-industrial levels at least once in the next 5 years. Now, while that doesn't mean that we will permanently exceed the 1.5 degrees Celsius limit specified in the Paris Agreement, the World Meteorological Organization is still sounding the alarm that we will breach that 1.5 degrees Celsius level with increasing frequency. As well as spying on your every internet action and giving you search results which favour its own advertisers, a major study has confirmed that Google cannot be trusted on political issues. The findings by All Sides News Bias Analyses found that 61% of 151 media outlets presented on Google News homepage over a 5-day period were all from sources which tended to lean to the liberal left side of politics. At the same time, only 36% were from the centre or non-rated news outlets, and just 3% were from conservative news sources. And when the study's authors used the search term election, they returned no results from centre or right-leaning media outlets in the days leading up to the 2022 United States midterms. However, 28% of the articles presented by Google News for the search term were from the left-leaning CNN, and 16% of articles were from the more extreme left-leaning New York Times. The findings confirm that Google isn't like the phone book. It's not impartial, but rather it pushes a socialist political agenda, sometimes subtly, other times more blatantly. And of course, Google aren't alone. In a 2021 court case brought about by journalist Steven Stossel, Facebook admitted under oath that its fact checks were simply opinion. The court was told that fact checkers are not unbiased arbiters of the truth, they're simply useful distractions. Paleontologists have described the new species of Spinosauroid dinosaur discovered in Spain. Dating back to the early Cretaceous between 127 and 126 million years ago, the new discovery has been named Proteolithus cinctorensis, the champion from the town of Cinctorrens, where it was discovered. The specimen, which is estimated to have been around 11 metres long, is based on fossil fragments including a right jawbone, a tooth, and 5 vertebrae. Spinosauroids comprise different groups of often semi-aquatic bipedal carnivores, some of which, such as the sailback Spinosaurus, grew larger than T-Rex. The new findings, published in the journal Science Reports, sheds new light on the origin and evolution of Spinosauroids across what today is the Iberian Peninsula. Based on the new find, the authors proposed that this new species may indicate that Spinosauroids appeared during the early Cretaceous in Laurasia, a large area of land in what is now the Northern Hemisphere, with 2 subgroups of the species occupying Western Europe. Spinosauroids may then have migrated to Africa and Asia as they diversified. Health authorities in Mexico are going to encourage greater use of traditional native medicines in the country's woefully under-equipped public health system. The head of Mexico's largest public hospital network says the department will hire 753 traditional healers. Tim Mendham from Australian Skeptics says it's the same formula used by Chinese and Indian governments to quell the clambering poor and sick in their countries.
Mexico, a country that has problems with medical infrastructure, especially in regional areas. It's not very well set up. Also areas where it's dangerous to set it up, considering crime levels and gangs and things. So therefore, in certain areas, there are few doctors, so they have to find alternatives. And what they'll move into is more traditional medicine in various hospitals and things like that, including hiring 753 practitioners of traditional massage and herbal treatment. And they're also bringing in people who are called curanderos, who are non-licensed healers who use bundles of herbs, smoke, alcohol, and eggs to draw sickness out of the bodies of their patients. Now, this is pretty fringe stuff, and obviously a lot of traditional medicine is pseudo-medicine. They're also bringing in midwives who use a traditional form of chiropractic medicine. Now, chiropractic and medicine are 2 words that don't go well together. Traditional chiropractic only goes back a couple of hundred years, so I'm not quite sure what traditional chiropractic is. Anyway, this is the sort of stuff they're saying they're bringing in under the approval of the President Obrador of Mexico, who's also the same person who claimed that he believes in mythical Mayan creatures. So there's a bit of a theme running here, which is rather concerning. But they're also bringing in doctors and things from Cuba. So really they're trying to pack out a very poor medical system, especially in regions and things, and they're using desperately anything, reverting to supposed traditional herbal cures and that sort of stuff. The same thing happened in China sort of way back when in the 40s or 50s, when their medical infrastructure was pretty poor, and they then, especially under Chairman Mao, promoted acupuncture as a medical treatment, mainly because there was a lot of people doing it. It was cheap, it was easy to do, and the medical system just wasn't set up to handle all the people who were coming in. So a lot of the promotion of acupuncture came out of a medical failing rather than a pro-acupuncture.
Meanwhile, Mao and colleagues kept using modern Western medicines instead.
That's right, yeah. I mean, this was just for the poor people. The mug punters of the Chinese community can have acupuncture that has very, very limited application.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC. A client met his banker to discuss opening a restaurant in a busy airport. In us, he found a partner that understood the importance of reaching for the sky. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac.